So the topic of this session is systems, and this is what I hope to give you, namely a system, or in this case a toolchain for generating transit maps from schedule data, so basically from scratch. My name is Patrick. I'm from the University of Freiburg. I work at the chair of algorithms and data structure of Professor Hannah Bast. And the tools presented here today are all based on work by Hannah Bast, Sabine Sturand, and myself. Okay, so the overall goal, of course, as I've said, is given some schedule data set represented here as this bag of trips. Of course, you can have schedule data in all kinds of formats, but let's just call it a bag of trips here. Render a schematic, a possibly schematic transit map from this data. So given this bag of trips, it will hopefully, the approach will hopefully generate a map that will look like this. So the individual subtasks or the sub-problems to this goal are, of course, very well researched. So there are many publications regarding the schematization. We have seen some approaches already today, some new algorithms to do this. There are many publications considering the optimal line ordering, so how you find the optimal line ordering on the individual segments like here, so that the number of line crossings or other optimization criteria is optimized. There's a lot of work on map labeling, of course, in general, but also on labeling of transit maps, labeling, integrated map labeling with schematization, and of course there's much work on aesthetic aspects. But this work here, there is, of course, in the tools I will present to you, there's, of course, a ton of interesting algorithmic work. But this presentation is not about the algorithms, but should be a hands-on presentation of a software suite to achieve exactly the goal stated above. So as an additional motivation, let me just tell you a story from my life, which I've experienced a few years ago, and which is also how I stumbled into this area. After my master's thesis, I was hired by a small company in doing some GIS stuff. And because I was young and naive, I immediately took the job, and it all went well for a few months. And then after half a year, my boss, who was and is a very nice guy, took me into a room and just told me about this new task they had secured from a very large customer. And he basically told me that we had to develop some web apps, and a subtask should be that the web map portal should display a map which was to be rendered from raw schedule data on a monthly basis. So it should be updated, the schedule data should be updated every 4 weeks or so, and the map should be updated. And it just told me, well, we just render it automatically, and you have maybe 4 to 5 months, and then we can show the customer something. And then he showed me a PDF of the maps we should generate automatically. Up until then, the maps were generated by hand. They were drawn by hand by professional designers. And this was the map he showed me. So some of you may already know this map. This is the network map, a schematic network map of the Swiss rail network. Each line is actually a train line, and the small numbers here and the colors depict how often this how frequent this line runs, and the numbers show you the exact minute they will start at this particular station. And naturally my heart stopped, because I had no idea how we should render this automatically, let alone how we should do this in 4 to 5 months. So we tried this for a while, a colleague and I, we tried it for maybe half a year, and we failed very badly. We didn't get anywhere. So after another year of similar tasks, I decided to go back into academia. But what did I take with me? Basically 3 things. The first thing was that in the world of professional schedule design, in the world of professional schedule planners, these people long for a tool to render such transit map, because of course this is a schematic transit map after all, just a very complicated one. They long for tools which can render such maps very quickly, automatically. The second thing I took was that people who have never tried to generate such maps, either by hand or automatically, typically greatly underestimate how difficult this problem is, because transit maps are basically everywhere, and people just assume, well, it's very easy to render them automatically. Of course, I quickly learned back then, this is how I stumbled into this topic, I quickly learned back then by reviewing the existing literature that basically every sub-problem of this task is NP hard, so it's just an extremely hard problem. And the third thing I took from my experience back then was that I noticed when reviewing the literature, the existing approaches, the existing algorithmic approaches, they all started at a point we didn't even get to after 6 months of trying. So the typical input data for research methods that you can find in publication is they all assume you already have a very nice clean graph embedding of a transit network. So stations are just very clean nodes and they are possibly labeled with some station label. And in between the nodes there are some edges, and the edges are labeled with the lines traveling through the edges and possibly a color of the line. But if you start from raw schedule data, this is usually what the data gives you. So this is an actual graph extracted from the network of the VAG here in Freiburg. So this is from actual schedule data, and this is how it looks like. So you can immediately see that it is impossible to render a nice looking map from this data. So there are all kinds of problems. For example, you have of course multiple nodes for a single station. So all the nodes you can see here, this is all a single station, a very large station at the city center of Freiburg. And of course the schedule data just models all the individual stops where vehicles can come to a stop. And in this case, I think it's 6 or 7 positions. And you have that many nodes plus an additional central node here, which is not connected to all of these nodes in any way. So you have, of course, overlaps, many overlaps. And the most striking thing that is missing here is, of course, you don't have the geographical line courses. They are often missing from the schedule data. So even if you wanted to extract a clean graph embedding of the transit network from this, it's basically impossible because you don't know that all of these edges here, they basically travel along the same tracks between this station and this station. You don't have the geographical line courses. So extracting this also is very difficult. And another thing that is missing here is, of course, the line colors, because they are also very often missing from schedule data. Where do you get them? Do you generate them automatically? But typically transit companies, of course, have line colors and they want them in their maps. So you have to either label them by hand or think of ways to get these. So our toolchain, as I've said, will start from raw schedule data. So we will start exactly there. We will assume that the schedule data is given as a GTFS feed. I know there are many other schedule data sets or formats, for example, VDB452 or HRDF, but for simplicity, we will limit ourselves to GTFS data. I will then show you a tool to extract the geographical line courses for a GTFS feed without geographical line courses. This tool is called pfaedle. Then we will show how we will have a look at how to extract a clean network graph from the GTFS data augmented with the geographical line courses. This is a tool called Topo. Then we will have a look at a line ordering optimization tool. I'm sure many of you are familiar with this problem. This is the LOOM tool, which just finds optimal line orderings. Then we will have a look at schematization. This is the octi tool. The schematization is optional. Of course, if you skip the octi tool, then what you get is a geographically correct map. And at the end, we will look at how we can render all of these intermediate graphs. All of these tools will output graphs. I will show you this in a minute. And this transit map tool here will just take such a graph, which is given as a GeoJSON format, and just render it into an SVG file, which you then can use to maybe further edit it or use it directly. So pfaedle is actually a standalone tool, and Topo, LOOM, Octi, and Transit Map, and some auxiliary helper tools I will quickly show you in a minute, are part of the LOOM software suite. So the code is available on GitHub. There is the pfaedle tool, and there is the LOOM software tools. And we will start right now with rendering the Freiburg tram network together. So I've prepared, here's some files. Basically, can everybody see this? Is this large enough? Great. So we have 2 files here. One is the Freiburg.osm file, which is just OpenStreetMap data for the Freiburg area, which I have downloaded. And we have this VAG Freiburg file, which is just a GTFS feed of Freiburg. So let's just extract this. Let's call this maybe Freiburg GTFS. So we extract the schedule data set, and I'm sure some of you are familiar with GTFS. This is how GTFS data looks like. It's just a list of text files. These are basically CSV files. And as you can see here, there's no shapes.txt. So in GTFS, the geographical line cursors are stored in a file called shapes.txt. This is missing here. So we can actually already extract a graph from this schedule data by using the GTFS to graph tool, which is contained in LOOM. And we want to generate a map of the tram network of Freiburg. So we just select via this -m flag the tram method of transportation, and we just give it the GTFS feed we have just extracted. And what it will now do is it will output GeoJSON, which we can just pipe into a tool or write into a tool. Let's call it Freiburg raw.json. And because this is just a GeoJSON file, we can just open it with QGIS, for example, and have a look at it. And just select this here. So this is how it looks like, and this file has exactly the problems I've just shown you. So you have great overlap here, many overlapping lines, many stations, and no geographical line cursors. So this is exactly where the pfaedle tool comes in. So what pfaedle does, it receives as input GTFS data without any shapes and additional OpenStreetMap data, and will generate a GTFS data set with the geographical line cursors. This is basically a map matching problem, and we use a hidden Markov model-based approach. If you're interested in the details, the publication is down there. And its usage is actually pretty simple. This is how you can use it. And we will do this now together. So what we do is we use the pfaedle tool. We give it the OpenStreetMap file as the -x flag, and we just give it the GTFS data set. And it will now generate the missing geographical line cursors for all the methods of transportation. And it has now written this directory GTFS out, which is again a GTFS feed, and it now contains this shapes.txt file, which just contains the geographical line cursors. So what we can now actually do is we can run this GTFS to graph tool again, but this time let's use the shaped GTFS feed. So usage is exactly the same. And the extracted graph will now look like this. So as you can see, we now have the geographical line cursors. The network looks much cleaner, but of course there's still overlap. So for example, you have all the lines, most of the lines travel of course in two directions, and there are two tracks. So you have now basically every line doubled. And of course there's also much overlap. For example here, where two tracks branch. Of course in reality, two tracks don't branch in a discrete way. It's a gradual thing, and you have all the intersection and the stuff all depicted here. So we can actually render this graph already in a transit map style. Let's have a look at how this works or looks. I mentioned the transit map tool. We can just use this and give it this raw GeoJSON file of the Freiburg network, and then it will output SVG, as you can see here. Let's just store this in this file here, freiburg.svg, and now it will just write this map, and we can look at it with an SVG viewer. Chrome can actually do this, and you can see this map now has many problems. You see clear overlaps here. There are many lines overlapping here. Here you have overlaps. You have extreme station duplication here. So basically all the problem of the input data are visible here in the rendered map. So how do we get rid of this? How do we get rid of the overlaps? How do we get rid of the station duplication and the duplicate lines? Well, this is exactly where the topo tool comes in. Now here the input is a line labeled graph. We just call it a line graph of a transit network. And the output is what we call a free line graph without any overlaps, which is basically the clean input you need for generating transit maps. So let's just do this. Let's just read in this raw file and write it to a file. Let's call it Freiburg topo.json. Now we can actually have a look at this in QGIS by just adding another layer. Sorry, this will take a few seconds. Okay, so this is now the graph, and as you can see, it is now very clean. You only have single edges between nodes. You only have single nodes for stations, and all the edges, which you can see here, it's very small, but they're all labeled with a line ID, a line label, a line ID, and a line color. And I forgot to mention this, the line color was also extracted from the OpenStreetMap data. pfaedle also can extract the line color, but in this case it wasn't actually necessary because the GTFS feed already contained the color. Okay, so now we can render this file here. Let's again use the transit map tool and now give it the topo.json file we just generated, and again write it to the Freiburg.svg file. Now if you look at it, it already looks pretty good because now you don't have line overlaps anymore. You have only single nodes for single stations. But of course, most of you have already noticed it. There are some unnecessary crossings. This is very ugly here. There is an unnecessary crossing hidden behind this node. And I think in this there is another crossing somewhere. I don't find it at the moment. But to remove these crossings, we have to find optimal orderings on the lines of these individual segments. And this is exactly where now the LOOM tool comes in. The input to LOOM is again any line graph in the GeoJSON format I've just shown you, and the output is a line graph in which the line label orderings are optimized. So this is of course a combinatorial optimization problem. If you're interested in how we do this, the publication is down here, and the usage is again very simple, just like the tools I've shown you before. Just put in the GeoJSON file, get an optimal line ordering optimized version of it. So let's just do this. Let's just use the LOOM tool with this topo file and output it into, let's call this opt.json. And now we can render this again. Sorry. Yes, and now the line orderings are optimal. So this is quite nice. So now, of course, this is a schematic mapping workshop. So what is missing so far is how do we actually get schematic variants of these line graphs? Well, this is what the octi tool is for. I won't go into any details, but this basically uses a grid-based optimization approach and currently supports ortholinear, or rectilinear, octilinear, or octilinear, hexalinear, and orthoradial layouts. We'll have a look at them in a minute. Again, the optimization approaches are described in these publications, and the usage is again very similar to the tools we have seen before. We just give it now this optimal, a line ordering optimized file, and write this into, let's call it octi. And now we can render this again. Well, let's actually increase the line width a bit, because I think the Freiburg map looks better if we increase the line width and the line spacing. Octi file, let's write this again into this Freiburg.svg file. Yeah, and now you have an octilinear map. So this is actually quite useful if you want to have a fast prototype of your map. Now you might prefer another layout. So let's actually use the octi tool again. Let's actually do it like this now. I will describe the pipe approach in a minute, but we can actually do it like this. So just output the topological file, just pipe it into octi. So this is now creating exactly the same map we have just shown as seen before, the octilinear map. And we can now use different layouts by using this -b flag. So for example, we can render an ortholinear map by using ortholinear for this, and then let's have a look in exactly. Now I have a rectilinear map, Oh, sorry, this was the wrong input file. This was the input file, which was line ordering optimized. So this should be the correct one. Yeah, now the line ordering is optimal. You can render hexalinear maps. Then it will look like this. So some people like this, I don't. It looks strange to me. And of course we have, this is a recent addition to this tool, we have an orthoradial layout. This is, if you remember the circular layout we have seen yesterday in the very nice new Cologne map. So if we use this, then it actually looks like this. So we get an orthoradial layout. We can actually add labels, although I should say that this is highly preliminary with the -L flag. And let's just increase the station label text size a bit, because otherwise you can't read them on this screen. So this should work if I haven't made a mistake. Yeah, exactly. Now you get line labels. So one thing I haven't shown you, let me just quickly show you, because I think this is a very nice feature. So if you go back to the octilinear map, this is how it looked like. So now you might decide, well, maybe I want to use this as an overlay over some existing geographical data set or some satellite imagery, and I need to actually approximate the geographical line courses between stations. So we also use the degree 2 heuristic, so all these stations are contracted before we schematize this. But you can actually tell Octi to respect the geographical line courses a bit, and you can do this by specifying a penalty. Let's just use 5 here. And now what we should see is, yeah, exactly. Now the map approximates a bit more the geographical line courses. You can see it up here, and well, let's actually do it a bit. Let's actually set it a bit higher. I don't know what happens if you set this to 50. I've never tried this. Now it all breaks. Yeah, exactly. Now you get a map which is very close to the geographical layout, but it doesn't look that nice anymore, because it also tries to preserve the octilinearity. And this is actually exactly how it is in reality. So this is kind of a loop here. And there are some other parameters which you can choose to make this geographically correct map look a bit better. Okay, you have already seen the transit map tool. I will skip this because I've already seen it. Just 2 remarks here. The SVG output has several benefits. One is, of course, that you can easily style the map via cascading style sheets. So in this GeoJSON file that is used as input for transit map, in this GeoJSON file, you can just specify additional CSS rules to, for example, I don't know, get a dashed line or something like that. I haven't prepared any examples for this. And another benefit of the SVG format, of course, is that you can easily edit these maps, because you can just open them in some SVG editor, for example, Inkscape here on Linux, but I think you can also use Adobe Illustrator or any other tool which can generate, which can edit SVG files. And you can select all the individual lines and just polish this map before publication. Another thing I want to show you, but I'm running out of time, is that you can use these maps nicely as a web map overlay. So this is, I think, let's actually show the label. Yeah, this is, I think, very similar to the map we have seen for Bonn just 2 hours earlier. So here we just use the SVG files as an overlay. This is Leaflet here, the map software, and Leaflet has just this SVG layer. And as this is a vector graphics format, you can of course implement stuff like highlighting lines or something like this. You can also implement click listener. We haven't done this here. So in the SVG output, all the lines have classes. So it's very easy to select a single line. Although these are all separate segments, it's very easy to select and highlight a single line via these classes by, for example, making it a bit thicker. Exactly. Yeah, you can also use the labels, of course. And this is also very easy. If you're interested in doing this, we also have code for this web portal. There's code available, although this code is not polished, so it might be a bit tricky to get this running. Okay, just a quick overview. The pipeline approach I mentioned earlier, you have already seen this. We took this seriously. Between each step, the tools of the LOOM software suite, the output is always GeoJSON and the input is also always GeoJSON. And this allows, of course, for easy modification and extension. So, for example, the map we have just generated, you could just do it with the simple call. So you use the GTFS to graph tool, call it on the shape GTFS data, pipe this to topo, pipe this to LOOM to find the optimal line orderings, pipe this to octi to find the schematic representation, and then pipe this to transit map to just output a SVG. So this single line will generate you the map I have just shown you. Okay, who is this for? Well, who do we hope this is for? Well, I think this could be useful for researchers who want to try their own methods but don't want to fiddle with all the stuff to generate actual line graphs which you can render and who don't want to do the actual rendering themselves. It may also be useful if you want to compare different methods using the same styling or the same rendering engines. It may also be useful for map designers for fast prototyping because, as I've shown you, you can edit the maps and polish them using any editor. And it might also be useful, as I've mentioned at the beginning of this talk, for professional people in schedule planning, just for a quick visualization of schedules. I talked to people who told me that it would be useful to show, for example, the effects on network extensions to other colleagues. So you should always end on a high note. I decided to end on a low note. What are the rough edges? What doesn't work? Well, there is of course a ton of stuff that I think doesn't work so well already, because all the tools here, they were initially prototypes for publications we have done, and we tried very hard over the last few months to make this production ready, but big quotes in production ready. So if you find any bugs in trying this, just tell me. pfaedle, for example, can only accept XML files for the OpenStreetMap files, which is a bit unhandy if you take very large OpenStreetMap data sets. All the tools I've presented here can only accept extracted GTFS feeds, which is also a bit unhandy because GTFS feeds typically come zipped. The labeling, as I've mentioned, is completely preliminary. And of course, for schematic maps, the labeling should be part of the schematization because you need some space for the labels, and we have not implemented this. This is the next big thing we have to do. One thing that is missing and that we would like to do is, for example, some pre-processing and the enlargement of high-density areas in the schematic maps to just make the map a bit less clustered. The schematic maps are based on a heuristic approach, which is a bit unstable, as all heuristic approaches are. So small changes to the input data may result in a completely different layout, and you suddenly think, what happened now? And of course, extremely large networks. So we have tried this for the London subway network and the New York subway network with the express lines. If you try to schematize these maps, they often show constraint violations because the heuristic approach simply cannot find a schematic version without any constraint violations. And of course, the ILP approach just takes too long. It usually takes hours or even days. Yeah, and another thing that is also missing and we would like to implement is tariff zones, that you can render tariff zones. I think this was already mentioned in some talk yesterday. And of course, the holy grail is an interactive map editor where you can just download a schedule data set. It will give you some a version of a schematic map, and you can just edit it, and it will help you do this. Okay, thank you very much. This is behind this link, you will find the geographically correct maps I've just shown you, and under this link you can play around with various octilinear or orthoradial and hexalinear maps. Okay, thank you very much.